so welcome to WebRTC Part 2, a stunning turn of events. This is the second part of my talk about WebRTC. My first one was back in October. So let's talk a little bit about what we're going to cover today. So last time we talked about the basics, like WebRTC, what is it? It's, oh, hold on, I'm not sharing my screen. Oh my God, so many things so many buttons to press. Present, entire screen. Yes, do it. All right, now we're going. So I know I'm presenting to everyone. Thank you. Hide this. All right, let's restart that. So welcome to RTC2, a stunning turn of events. This is my second talk. The first one was back in October. So last time we talked about WebRTC. What is it? And it's an API that you can use in the browser in JavaScript to get access to a user's webcam and microphone. And then you can use it to send that webcam microphone feed over the internet to other computers, and you can use it to build video conferencing apps in the browser. Um, so last time we just covered, how to that first part, how to get the camera and microphone, and how to combine that with other APIs in the browser, like locally, sort of like things like Canvas, WebGL, Web Audio API, and the Media Recorder API to make cool art stuff. And in that talk, I mentioned these three guys up here. Get user media, which is how you get the webcam and microphone. The media stream, which is the data type that you get back. And enumerate devices, that's a way that you can determine which webcam or microphone you're going to use. And I mentioned that there was a whole other part of WebRTC, the dark side. You never go there, Simba. And today we're going there. We're doing all of it. And we have to. We can avoid it no more. And the reason why we're going to go through all of this is because this is one of the most difficult technologies to get started with. But once you get like over the hump of the beginning, there's a lot of really cool stuff you can do. So I'm going to show a quick demo of this is a bit of the trailer from a recent online show that I worked on back in October. It was called The Battle of Broken Mirrors. It was an online interactive immersive theater show. And the app for this was entirely browser based and could be used on a multitude of devices. We had people coming in from San Francisco on their phones and whatnot. We had actors coming in from all over the East Coast. And this whole thing was enabled by WebRTC. So the reason why it's important to start learning about this stuff is because there's a lot of really cool like powers in the browser that you can unlock that have never been possible before, but are now. So in terms of what we're going to cover today, we're going to start with the bad part, the problems with peer-to-peer communication and NATs. We're going to talk about what those are. As you can tell from that glacier diagram, there's a lot of alphabet soup, a lot of acronyms and things going on. We're gonna have to talk about ICE, stun, turn, and SDP. And this part is gonna be, very heavy on jargon, very heavy on history, and we're gonna have to learn a lot about like the networking stack that underlies how our computers work in order to really understand like what is this problem and how is WebRTC solving it exactly. Once we get through all of that, we get to the good part. I've got some demos, and when we're done, I have links that I can post where you can download them on GitHub and use them yourself. I'm gonna start by showing you how to connect two browsers on the same computer. Then we're gonna step it up two browsers that are on different devices but on the same network. And then I'll finish up by explaining a little bit about how to connect a bunch of people from anywhere in the world. So we're going to start by talking about the problem that we need to solve here. So if you've heard of WebRTC before, you may have heard WebRTC can work peer-to-peer, and this is really cool. You can take audio, video, or even arbitrary data like files or text, and you can send them directly from one computer to another with no server in between at all. There's an asterisk there, and we will get to that. So, okay, how do we do that? How do we connect two computers? Well, in order to connect two computers, they need to know each other's IP addresses. So, In order to learn about why this is a problem, we're going to need to take a journey back in time, back to the 1980s. So yeah, it was the good old 1980s. Computers were big and expensive and slow, and Bill Gates was saying, like, hey, who's gonna need more than 640 kilobytes of memory? Am I right? I mean, what would you even do with a megabyte of memory? That'd be preposterous. Like no one's ever gonna need that. So this was not a time that was known for long-term planning or good decision making, for that matter. And so that might have been what led them to create this thing, IPv4. So in 1981, the Internet Engineering Task Force debuted something called IPv4. This was a system for coming up with unique addresses for computers. They had a bunch of computers, they were starting to connect them together, and they needed a way for each computer to have a unique address that no other computer had. So this system involves giving each computer a number. That number is composed of 4 octets. An octet is a number from 0 to 255, and it's called an octet because it can be represented in 8 bits of binary. So if you've got 4 of these, and you do the math, how many addresses can you make with this system? Well, 256 to the 4th power is 4.3 billion unique addresses. Now, I mean, this is the system that was designed in 1981. It's the one that we're still using today. I mean, surely that's got to be enough, right? I mean, are you telling me that like half of the world is going to own a computer? No way, you know? And like, are you really telling me they're all going to be on the same network? Nah. This system is flawless and perfect, and there's nothing that could possibly go wrong. And they were so confident in this that they immediately started carving up large sections of the address space for technical use, and then sold off large tranches of the rest of it to U.S. government agencies and multinational corporations, some of which are no longer even in business. And eventually, they did start to realize that this was going to be a problem. A bit late, but better late than never, I guess. In 1998, the IETF gave it another try, and they came up with the IPv6 standard. This is a much better one. As you can see here, it has 16 octets instead of 4. It uses colons so that it can never, instead of dots, so it can never be confused with IPv4 by any device. It uses hexadecimal numbers instead of base 10 numbers, so that you can represent a larger address space with fewer characters. And it's also got like a shorthand notation and even like a backwards compatible thing for working with IPv4 addresses but representing them in IPv6. It's a very well thought out system, and it can represent about 3.4 times 10 to the 38 addresses, which is about approaching the number of atoms in the observable universe. So I would say it's probably sufficient. So you'd think, clearly this is a much better system. It must have taken off, right? Well, not quite. The thing is that in order for IPv6 to work, let's say that I have a program on my computer and I want to connect to a program on your computer. Those programs both have to support IPv6. The network stack of the operating system needs to support it. Sometimes even the firmware of the network card needs to support it. And then every switch and router in between the two computers has to support it, including the ones in your house and the ones that are supplied by various the ISP and infrastructure and backbone stuff. And if any one link in the chain does not support IPv6, it's over. We just use IPv4 instead. So this did not really take off much until the 2010s, because the 4G standard says that all phones that are on 4G networks must use IPv6. And so we started seeing a slow rise. And hey, we might get to 100% coverage in a decade or so. Surely that'll be fast enough to avoid. Oh, oops. We're running out of IP addresses. In fact, we've basically kind of run out. And so IPv6 isn't coming up fast enough. IPv4 was clearly going to be exhausted way before we could switch. So the powers that be had to come up with a way to ration the IPv4 addresses so they wouldn't all get used up. And so they came up with this, NAT, Network Address Translation. So this is a system where they were thinking, hey, so we can't give every computer in the world a unique address. We don't have enough addresses for that. But what if we didn't need to give as many computers addresses? So they started doing things where If you get a cable modem from Comcast, that modem gets an IP address, but all of the devices in your house do not. Basically, that cable modem tries to stretch that one IP address over all the devices in your house. And so anytime that one of your devices, makes a request out to a server, it appears as though it's coming from the address of your router, like this one here, 209.133.2901. And that means that if somebody wants to send a message or a request to a computer that is on your home network, like your phone or a laptop or something like that, and if it wants to send that directly, um, there's no way for it to really do so because none of those devices have public IP addresses. Now, there are sort of hacks to get around this with things like port forwarding and technologies like WebSockets and long polling have ways of hacking through this sort of. But for the most part, yeah, if a device is behind a NAT, if it's in your home Wi-Fi, you probably can't send stuff to it from the outside world directly. Um, so there are some people who do get actual public IPv4 addresses. So as I mentioned before, cable modems or other modems, things that are between like your house or your office and the internet. They will use one IP address as I described and try and stretch it over all the devices on the network. Um, Now, some people who have money will buy IP addresses because you can do that. They are, a scarce commodity and can be purchased. Um, and so, devices that are on an enterprise network or VPN, if you work for a large corporation and you go into the office and you log into the special Wi-Fi, you might actually get a public IP because the company may have paid for a pool of IP addresses to hand out to employee devices. The other place where IPv4 addresses are actually like public ones actually do get used is servers. If you make a server in AWS, that server is going to have an actual IP address. AWS has bought up tons of them, and servers really need them because servers are receiving requests from the outside world all the time, and they can't, do the sort of weird hacks that our local devices do. Um, so yeah, so IPv4 addresses, a lot of computers just don't have a public one that other computers in the world can use to access them. So if we got two devices, how do we connect them? Well, there's a bunch of ways that it could work. Let's say that you've got two cell phones that are on a 4G network. They can just use their IPv6 addresses and connect to each other, just like that. That's all it takes. If you've got two laptops that are on the same home Wi-Fi network, they can use their local IPv4 addresses. If you have the local IPv4 addresses often look like 10.0.0. something or 192.168.0. something. That's an IP address that's only valid like within your local network. But if both devices are on the local network, that's fine. Laptops that are on, maybe in two different corporate offices, they might have public IPs and they can talk straight to each other over IPv4. Now, if you've got laptops that are on two different home Wi-Fi networks, like I said, there's not going to be a good way for them to connect. And we'll get into what happens there in a moment because WebRTC has a way around that, but it's unfortunate. Now, so I just laid out four different ways that like two devices could connect to each other. There's lots of different combinations and permutations of these things. And when you want to connect two arbitrary devices, you need to figure out what's the best way to do it. So you need to figure out how to establish connectivity on the internet, and to do that, you will need ICE, or Internet Connectivity Establishment. So ICE is a process where you try and figure out how the two computers are going to connect. And that process basically involves, we're going to write down a list of all the ways that our computer can be contacted by another computer. We're going to look at our local IP address, both the IPv4 and IPv6, just to be sure. And we can get these just by asking the operating system. We are also going to get our public IP address, and this is where stun comes in. I'll explain that in a moment. And if none of those work, if we're two laptops that are on different home Wi-Fis, we're going to pass in a list of relay servers that we could use if those first two don't work. And this is where turn comes in. I'll mention that in a moment too. So each of these possible ways that you could connect is called an ICE candidate. An ICE candidate is a way that another computer might be able to reach us. So I mentioned stun a moment ago. if your computer is, let's say it's on an enterprise network, it looks for its local IP address. It's 192.168.0.118. But then it also wants to see, like, maybe I have a public IP. Let's find out. So the way that you do that is you're going to need to talk to somebody who's outside of your network and then ask them, hey, where did this request come from? And to facilitate this, there are servers out there called stun servers. It stands for Session Traversal Utilities for NAT. And they are specially designed to just handle these really simple requests. You send a request saying, hey, what IP address sent this? And they say back, oh, this request came from 172.148. Whatever. And now you write that one down. That's another way that you might be able to be contacted. If you're on an enterprise network, that might work. If you are on your home Wi-Fi, the address you get back is going to be the one for your cable modem. It's not going to work. But we write it down anyway. We write everything down with ICE. Now, like I said, if IPv6 isn't going to work and you're not on an enterprise VPN, and you've got two computers that are both behind NATs, you're going to need to use a turn server. So what this means is we're basically like, hey, there's no way for these two computers to directly connect to each other. We've tried everything. There's just nothing. So what we're going to do is we're going to buy a server out there in the cloud somewhere, and we're going to say, hey, client A over here, they're going to send their video and audio to the turn server, and the turn server and client B is going to send their audio and video to the turn server. And when client B sends their video in, the turn server replies with client A's video and vice versa. So the turn server is basically just like proxying both ways, and it's streaming all of the audio and video in both directions. This is expensive. Stun servers, there's public free ones that you can use, but turn servers you're going to need to either get your own or pay for a service that has them, because they use up a lot of bandwidth, unfortunately. And this is sort of the lie of WebRTC, is people say like, oh, the two computers can talk without a server in between. But if they're behind two NATs, which is a lot of people, they can't, unfortunately. Now, with IPv6 becoming more usable all the time, there are less and less times where we need turn servers. But for the foreseeable future, this is something that we'll need to factor into anybody who wants to make a business around like a video conferencing app that uses WebRTC. You're gonna need turn servers. But as I'll get to in a moment, if you're trying to do like little things around your house, you can get away with a lot of stuff without using these things. So we have a couple more things in the bad part, and then I'll get to the fun stuff. So we've written down our list of ICE candidates, and we need to send them to the other computer. Now, this brings up an interesting question. Well, this whole process has been about, how do I connect the two computers? How do I send something from one computer to the other if they don't know how to connect to each other? So SDP is the protocol where you write down a message to send to the other computer. But how you send that message, which is just like a string of text, it's up to the developer to figure that out. You could use a signaling server in the middle. That signaling server would pass the message to the other user, and then would get out of the way and allow them to directly connect. You could also email it to the other person and then have them just paste it in, which is what we're going to do in a minute. You could copy and paste, or you could send it in a text message. The SDP is just plain text, so it's amenable to all that kind of stuff. Basically, the session description protocol involves writing down the ICE candidates as a string of text, somehow sending it to the other computer as what's called an SDP offer. The second computer looks at that offer and it says, let me try each of these ways of connecting to the other computer. And it goes, that one doesn't work, that one doesn't work, ooh, this one works. And it sends back an SDP answer with a list of the ones that do work. And once computer number one receives that SDP answer, now the two computers can connect. So, to review, ICE is the process of figuring out how a computer can be contacted. Stun is a way to find out your public IP address by asking a server on the public internet. Turn is a last resort measure where you send all of your data through a server on the public internet and the two computers can't connect directly. SDP is the process of exchanging the ICE candidates between computers. and involves an offer and an answer. So I think that's all the vocab that you need to sort of understand what's going on. Now, the good news is that because of the way that WebRTC is built into the browser, a lot of this laborious stuff I just described is like handled for you automatically by the browser. The browser hits up the networking stack and gets your local IP addresses and hits the stun server for you and writes the SDP itself. You do need to know how this stuff works though, because if you're trying to build an application on top of this, you need to know that this is a hard problem and like the sort of shape of the problem so that you can figure out how to best solve it for your situation. So, all right, on to the good part. I've spent this whole talk explaining how WebRTC doesn't work, and now we're going to show how it does. So, this is a demo application called Serverless WebRTC. And it is actually serverless. There are no turn servers or signaling servers involved. There's nothing up my sleeves here. We are going to do WebRTC with no server. Well, except for Slack's server, which I'm going to use. Anyway, you can download this yourself. I forked it from this fellow over here, CJB. I've updated it because it was written back in 2013 using an older version of the spec. It's now updated and it should run on Chrome and Safari. And if I refresh here, it should show the new. Yeah. To install it, there's no actual dependencies. I use browser sync to fire up a server. So if you want to use that, you can use npm install and then just do npm start and away we go. So let's go over here. We're going to do npm start. Fire up browser sync. All right. So the first thing we're going to do is we're going to connect two browsers that are on the same computer, just to sort of show like the very simplest case. So I'm going to have Chrome over here, and I'm going to have Firefox over here. So let me get these snapped in. And I'm going to open their dev tools as well so that we can see what's going on there. And let's get web developer, web console. All right. So over here in Chrome, I'm going to start the whole thing. I'm going to create a room. And boom, let's see what happened here. We just grabbed it. The Chrome just went and got a whole bunch of ICE candidates. And then once it got all those ICE candidates and it was done, it wrote up the SDP offer right here. So this is it. This big old thing of text. It describes all the ways that you could connect to this client, as well as a bunch of stuff about like video and audio codecs that are supported. You could dive into this thing and learn a lot about how your computer or your browser works. But we're not going to do that right now. We're going to copy this, and we're going to go over here and click join, and we're going to paste it. I'm going to say allow. I have two webcams, so hold on. You'll be able to see that there's two people sort of talking to each other. All right, so over here, yes, I sent this, and yes, I pasted it. All right, now we got our SDP answer. So I'm going to copy it, paste it over here. And now we're connected. So this one over here in the upper left is that is my local feed in Chrome. Upper right is my local feed in Firefox. You can see because they have different white balances. You can see sort of like that these are two browsers talking to each other and sending audio and video back and forth. I have muted the audio, but the video is there. There's also down here at the bottom a feature of WebRTC called data channels. So I can say hello world. And boom, it shows up over here. So you can use this to send data. That data could be text. It could be a file. The file thing doesn't work very well right now, but you could. In fact, people have built BitTorrent clients on top of this protocol. You can do that because it is peer-to-peer. So with all of that settled now, we've got two of the same. We have two browsers on the same device connected. That's cool. It's nice to see that this works, but it's not particularly useful. So now we're going to try and connect two different devices. So I've got my phone over here, and I am going to try and connect to it from my desktop. Now, here's the thing. WebRTC requires that you use SSL. And that means that you're going to need, or HTTPS. If you're on localhost, it does not, but we won't be on localhost when I'm on my phone. I'm gonna have to use my computer's IP address here. So this one will actually need HTTPS. So in this Git repo, I have a little thing down here, a little thing you can use, npm run serve :SSL, and if we do that, it uses a self-signed SSL certificate. And I tested this earlier today, which is why it's not doing it now. But normally when you do this, a big warning will come up and it'll be like, "Hey, are you sure you want to go to this website?" Just like hit like more information. Yes, I really want to do this, and then you're good. So I'm going to create a room. So let me open DevTools again here, just so everyone can see what's going on. I'm going to create a room, and now I've got. Oops, hold on. And now I've got my offer, and I got to get it over to my phone. So how am I going to do that? Well, this is where I go over to Slack and send it to myself. And now over here on my phone, I'm going to go into Slack and I'm going to copy this message. And now I'm going to hit join and hit allow. Yes, I want you to have my camera. And now, come on, paste. Okay, I pasted it. All right, and now it's giving me back another SDP answer. So I'm gonna double tap here and do select all, copy. Yeah, I sent it. And then over here, yes, I sent it. Oh, hold on, I need to send it to myself in Slack. So, all right, that. I'm gonna go over to Slack. I'm gonna copy all of this, the answer, and paste it in here. Okay, I pasted it, and hey, there we go. So now I'm talking to you on my phone, and yeah, so you can connect two devices to each other, and this can be like really useful for things like if you, I don't know, if you want to rig up like a baby monitor or something, you could set up a web app like this, leave like a tablet in the baby's room, and then you're sitting downstairs, you know, like watching TV. You got your laptop and you've got a video feed with audio in case baby wakes up or something like that. You could use it to make a security camera. You could use it. I've used it for a lot of live streaming during theater shows and stuff where I'll have you know, one person in another room in the theater broadcasting video that gets, you know, projected onto the screen. So there's a lot of really cool stuff that you can do, even if all you're doing is connecting over the local network. And so I think that's why I think it's cool to sort of learn this stuff because there's a lot of really cool stuff you can unlock. Now let's say that you want to take it a step further. This is one of the last things we got here. So let's say that you want to have multiple people talking to each other, not just one-on-one. Let's say that you have like 5 people who want to be in a room together. If you try and do that peer-to-peer, even if you don't have turn servers, if you're just, I don't know, 5 phones or something, if you look over here and see where it talks about mesh networks, when you, if you try and use WebRTC in a peer-to-peer manner, what'll end up happening is you will need to like send out 4 copies of your stream, one for each of the other participants, and you're going to be receiving 4 streams. And that means that there are total, there's like a ton of, there's like, you know, 10 connections going around and stuff. But also a lot of people have very slow upload speeds. And so this is like a real tough thing because it means that you need to upload, you know, 4 times as much video as you should. So a lot of people will recommend using an SFU or a selective forwarding unit. MCUs are complicated and I won't get into them right now, but SFUs are a great way to do this. This is how I've done it for all the shows that I've done. The one that I recommend is called Janus. It's free and open source. I think it's AGPL or maybe it's GPL v3. And it is Yeah, it's built by a startup called Meet Echo, but you can deploy it wherever you want for free using Docker or whatever. You do need to get into like DevOps stuff because you're going to need like, SSL certificate management and other things like that. But if you want to just try this out and see how it works, you can click here on demos and go to Echo Test, hit start, and oh, hold on. I suppose their server must be down. Oh, there it goes. So you can do this. What this is doing is it's capturing my audio and video, sending it to their server, which acts as if it's another browser talking over WebRTC. And then that server takes the video and sends it back to me. So on the left is my local feed, on the right is my feed after it's been bounced off the server. So with that, you can then see, like what, how this thing works. You can also, I'm not going to click on this right now, or what? Yeah. There's this video room. If you go in here, there's only one room, so there will probably be other people who are trying to test Janice who will show up in the room. I'm not going to do that right now to respect their privacy, but it's kind of funny. Um, so yeah, so that's what I've got, I think, for today. So yeah, thanks for watching. You can check me out on Twitter or GitHub. I'm going to post the links to all the things I just talked about in the Slack, including my slides. And yeah, that's all.